Hi, Richard.
Hi, Muccio.
Okay, I just started the live stream on YouTube. Okay, so I think it's probably a good idea to start now. Hello. Hello, everybody. Hello, everybody. Welcome to the Gaussian Process Summer School 2020. It's really special circumstances this year. We usually had the school with around 70 participants or so, Sheffield. So the background that I have at the moment is the City Hall here in Sheffield. And this year, for obvious reasons, we couldn't go ahead with the standard format. But the good thing is that because we're doing the online version, then now we can receive many more people. And that's really good for Gaussian processes, I suppose. So yeah, so probably you have already read the guidelines. In the guidelines, we explain sort of the format of the school. We're going to have a series of lectures, and in the afternoon, we're going to start with a lab session. And at the same time, we're going to have in parallel sessions, we're going to have 2 roundtables with the speakers of the morning. So we're going to have today a round session with Richard, and then another one with Nicola. And then we finish the day with another lecture. Today, we're going to have Andrew Wilson joining us from the States. Then we have decided to use the Huba app this year because I think it's a good way for promoting interactions and networking. So I would really suggest that you try to get to know other people using the Huba app. I've seen that already people had set some meetups. And I could encourage you to try to do that. It's a good opportunity, and it's a way to sort of compensate for the fact that we are not face-to-face this year. So I hope you enjoy the app, and as I said before, try to make the most of it. So this year has been really special for the summer school because we have more than 300 people registered. We actually still have people registering this morning. I think one of the issues with having a face-to-face conference usually is space. And that has been also our case in the summer school, but we are not restricted this year. So that's really good. So without further ado, I think we're gonna start this school now. So the first lecture of the day is by Professor Richard Wilkinson, who used to be at Sheffield until 3 weeks or 2 weeks ago. So he moved now to the University of Nottingham, and Richard is going to be giving us an introduction to Gaussian processes. So Richard?
Okay, thank you very much, Muccio. Welcome, everybody. So I'm not quite sure how many summer schools there have been. I think it's been going since 2010, perhaps. I think 2012 was my first one. It's probably the 7th one in a row I've spoken at. But like all the others, unlike all the others, this one's remote. So rather than kind of doing a nice brewery tour and so on, we'll have to figure out how to socialize online. So this talk is really basics of Gaussian processes. So I'll start by kind of reminding you of some basic details about Gaussian distributions, particularly about multivariate Gaussian distributions, and then we'll move on to defining Gaussian processes. So the process is different to distribution. And then the rest of the talk really is just repeating myself in multiple different ways. So I'm going to give different motivations and derivations around Gaussian processes, but I'll do the same thing several times. I'll give several different motivations and several different derivations, and just try and give you some kind of, well, allow you to see the different ways people think about GPs. And then Nicola, in his talk later this morning, will do some more of the same, okay, and give some more detail on kind of the nitty-gritty bits. And then I'll finish with just some of the difficulties of using Gaussian processes. So this is, believe it or not, the first seminar I've given over Zoom like this. So if I go too fast, if I talk too fast, if there are things that are unclear, just interrupt me. Okay. So Will is monitoring the questions. So please just raise your hand, ask a question, and Will's going to shout out and interrupt me, and I'll try and take questions as they come in. Okay. But I'll pause halfway through for people to ask questions as well. Okay. So first of all, then, something that everyone should know is just the boring old kind of the basic univariate Gaussian distribution. Okay. So let's suppose we've got a random variable, y, so it's a scalar quantity, just a number. Okay. And let's suppose it's a random variable and that it's got a Gaussian distribution. So we characterize the Gaussian distribution or normal distribution by its mean, which I called mu here, and its variance, sigma squared. Okay. And so if we look at the distribution of a Gaussian random variable, we can write down its probability density function, its PDF. Okay, so that's given by this form here. So it's an exponential with a quadratic in. So it's got a kind of key characteristic here. It's got y minus mu squared. And the variance just scales it. Okay. And that gives us this classic kind of bell-shaped curve here. We can also think about its cumulative distribution function, which is the probability the random variable capital Y takes some value less than some other quantity. Okay, you get this kind of classic looking sigmoid shape, this S shape. That's not known in closed form. So why do we like Gaussians? Okay, well, let me just say so before we move on. To generate a Gaussian that has mean, mu, and variance sigma squared, all we need to be able to do is generate a Gaussian that has mean 0 and variance 1. Okay, if we can generate a Z that has mean 0, variance 1, then to generate any other Gaussian, all we need to do is scale it by its standard deviation, so multiply it by sigma, and add its mean. Okay, and that converts a normal one random variable to a normal mu sigma squared random variable. Okay, so this is all familiar, I'm sure. So why do we like Gaussians? Why are they convenient to use? Why are they used all the time in statistics and machine learning? Well, it's primarily because they occur naturally and because they are mathematically easy to work with. So one nice property that we'll rely upon particularly is that the family of Gaussian distributions, normal distributions, is what we're going to call closed under linear operations. We'll talk about this more later, but in other words, if you take two Gaussian random variables and add them, you get another Gaussian random variable. Okay. If you multiply a Gaussian random variable by a constant, it's still Gaussian. If you add a constant, it's still Gaussian. So you can do lots of things to Gaussians and they remain Gaussian, which is a nice property. Then there's the central limit theorem that says if you add up a whole load of random variables, then under some mild conditions, if they're independent, identically distributed, okay, then no matter what their distribution, the sum of them, or the mean of them, will tend towards a normal distribution. So in nature, we get lots of processes that occur by sums of things, okay? And naturally, if you have enough things in that sum, it'll start to look Gaussian. Another interesting fact, which I didn't know till last year preparing these slides, is that the Gaussian is the distribution that has maximum entropy of any distribution with mean mu and variance sigma squared. So if you think of all the distributions that have mean mu and variance sigma squared, then in some sense, the one with the largest entropy, or the most surprising distribution, if you like, is the Gaussian. Okay. So this arises in the kind of maximum entropy principle, where if you don't know a distribution, you should choose the distribution that has the largest entropy. So the Gaussian appears kind of naturally there as well. They're infinitely divisible, if you know what that means. We have that if y and z are jointly normally distributed and they are uncorrelated, then they're independent. That's not true for any other distribution. So if y and z are uncorrelated, then they're independent. That only holds if they're Gaussian, okay, which is a nice property. And finally, lots of statistical procedures we use have a Gaussian interpretation. Okay. So imagine we're trying to fit a model f of x, a regression model that has some parameters beta to data y, and we're doing this by minimizing the sum of squared errors. So we look at the difference between our prediction from f and our data, we square it, okay? And we're just going to choose our model beta, our f beta, okay, to minimize that sum of squared errors. Then, okay, there's no statistics there, there's no distributions assumed at all, but it turns out that doing this least squares procedure is equivalent to doing maximum likelihood estimation, where you assume you have got Gaussian errors. Okay? And we like doing things with squares in because they're differentiable. Okay, so there's lots of statistical machine learning procedures that use squared loss, and they often have an interpretation that is statistical, where you've got Gaussian errors involved. So there are lots of occasions where Gaussians appear naturally in statistics, machine learning, okay, and so that's why we like using them. Okay, so that was univariate Gaussians. Multivariate Gaussian distributions are where we've got two or more random variables. Okay, so again, this should still be familiar to most of you, but we say that y in Rd, so a d-dimensional vector y has a multivariate Gaussian distribution, and to define that distribution, all we need to do is define its mean vector, mu, which is another vector in Rd, and its covariance matrix, which is a d by d matrix. Okay. And we'll write something like y twiddles has a normal distribution, dimension d, with mean mu and variance sigma. Okay. So if we just write out the details in a two-dimensional case, we've got our random variable y has two components, y1 and y2. The mean has two components, and the covariance matrix is a 2 by 2 matrix. The diagonal terms give the variances of the individual components. So sigma 1 squared is the variance of y1, sigma 2 squared is the variance of y2, and the off diagonals give the covariance. So the covariance between y1 and y2 is the correlation rho times the two standard deviations. Okay, so that's how we interpret these things. And its probability density function is pretty much the same as before. It's still a quadratic in y. Okay, so it's e to the quadratic in y. So its log likelihood is quadratic in y. So we've got e to the y minus mu transpose sigma inverse y minus mu. Okay. So let's just look at some pictures. So these are the scatter plots of 1,000 random samples from a two-dimensional multivariate Gaussian distribution. So I've given the distribution a mean 0 here, and its covariance matrix is just the identity here. So the variance is 1 and 1, and they're uncorrelated. You've got zeros here. So you can see these points scatter. And what we can do is look at the marginal distribution of y1 and y2. Okay. And one of the nice properties of Gaussians is that if we just look at the marginals of a multivariate Gaussian, they will be Gaussian as well. So jointly, y1 and y2 are Gaussian, but if I just look at y1, I get a Gaussian distribution with mean 0, variance 1. If I just look at y2, I get a Gaussian with mean 0 and variance 1.
Reg?
Yes?
Could you just clarify, what does entropy mean in this case?
Entropy is, you can think about how uncertain it is. So you can look up the definition, but it's something like the integral of log p of x dx. So it's an information theoretic concept, but you can think about how uncertain the distribution is. Okay. It's not an important point, so I won't linger on it. Look at the Wikipedia page. Basically, the point is that the Gaussian was the most uncertain of any distribution with a given mean and given variance. Okay, so this is a multivariate Gaussian with the mean 0, 0 and covariance identity. Let's change something. Okay, so if we change the mean, we just shift the cloud up. Okay, so it's centered around 0, 0 before. Now it's centered around 0, 1. So the cloud's just moved up a bit. And I've changed the variance of y2 to be 0.2. Okay. So before the variance is 1, so it's more spread out. I've changed it to 0.2, so it just has a smaller variance. So it just shifts the cloud. The red lines here are just ellipses containing 66% and 95% of the points. Okay. And because y1 and y2 are uncorrelated here, the ellipses are in the direction of the axes. Okay, so they go up and down, left and right. So let's introduce a correlation. So now the variance matrix has got 0.9 over here. So we've got a correlation of 0.9 between y1 and y2. And you can see what happens now is we get an ellipse that isn't parallel to the axes. If you tell me y1, it gives me information now about y2. They are no longer independent, they're correlated. So if you tell me y1 is -2, it gives me a good idea that y2 is likely to be negative as well. If you tell me y1 is 3, it gives me a good idea that y2 is likely to be large, or around 3 as well. Okay. If we shrink the covariance matrix, just multiply it by a constant, okay, it doesn't change the direction of these ellipses, the direction of the clouds lie in, it just shrinks or expands these this cloud of points. Okay, and if we make the correlation really extreme, so I've made it up to 0.99 here, we start to get a very thin band of points. And if I made the correlation really close to 1, so instead of 0.99, 0.9999999, all the points here would start to lie on a line. Okay. Okay, so that was in 2 dimensions. And we want to think about Gaussian processes, which are going to be infinite dimensional. So let's start to build towards that. So I'm going to show you first the same plots as these, like scatter plots, but I'm just going to plot them slightly differently. Okay. So in 2 dimensions, instead of a scatter plot where I plot y1 on the x-axis and y2 on the y-axis, so you get plots like this, I'm just going to have an index along the y-axis. So I've plotted all the y1 values where the index is 1, and all the y2 values where the index is 2, okay? And the y-axis here just gives the value of the random variable. And then I've joined up the 2 points. Okay? So this grey point up in this top corner here, that's got high y1 and high y2. And I've joined the 2 points here and joined them with a line. Okay. And we're going to do this now in more than 2 dimensions. So let's think about 5 dimensions. So I've just picked a mean vector that's 0 and a correlation matrix that looks like this. And now my points live in 5-dimensional space. Each sample from this multivariate normal distribution is 5-dimensional. And I can't plot in 5 dimensions. So what I've done instead is plotted the first value where the index is 1, the second value where the index is 2, third value, index is 3, so on. Okay, and then join the points. So this red line represents 1 point in 5-dimensional space. Blue line, another point in 5-dimensional space. Okay. And if you look at the covariance matrix up here, because these correlations are all high, the first y1 is highly related to y2, and the correlation is 0.99. Okay, they tend to be similar to each other. So if y1 is high, y2 is high. Okay. And similarly, y1 is still highly correlated to y5. Okay, a bit less than before, but it's still 0.96. So the 5th value is still highly correlated to the first value. Okay, each line here is 1 sample. So that's 5 dimensions. Let's skip ahead to 50 dimensions. So I've got a mean vector that is all 0 still, and I've just continued on my covariance matrix. So I've got 50 points, okay, and the correlation just ticks down through these variables. Okay. And now my index, I've got 50 different indices on here, and I've just joined them all. So each line has 50 points on, and I've joined them up. Okay. So this is how we're going to think about Gaussian processes. We can think of them as models of functions. Here, I've got 50 points. I've joined them all up so they look like a line. Okay. We can think of a function as being an infinite dimensional vector with a continuous index. Okay, we'll explain this a bit more on the next page. But instead of just having 50 values on this line, I could specify its value everywhere along this line, and that would tell me the function everywhere. Okay. So that's what a Gaussian process is. It's an infinite dimensional distribution over functions. And all we need to do to get from this kind of multivariate Gaussian distribution in 50 dimensions is to think about the indexing, which I'll explain now. Okay. So before we think about Gaussian processes, what's a stochastic process? Well, a stochastic process is just a collection of random variables indexed by some other variable. Okay. So my index, I'm going to call x. Okay, x lives in some set, curly x. You could think of that being the real line, the interval 0 to 1, or like in the previous slide, just the numbers 1 to 50. My index set here is 1, 2, 3, 4, up to 50. Okay. But in general, we could have a more general index set. A random variable is just a collection, a stochastic process is just a collection of random variables indexed by x. Okay. So usually, and everything I say today, x will be some subset of Rn or Rd, okay? And y of x is just going to be a scalar on the real line, a real valued scalar. And we can think of y as a function of x. Yeah? That's how we think of functions. Y is a function of x. If our index set is infinite, okay, an infinite number of elements of our index set, then y is going to be an infinite dimensional process. Okay. So when we had distributions, we had a finite number of indices, but for processes, we can have an infinite number of index values. Okay. So to understand stochastic processes, all we need to understand is what are called the finite dimensional distributions, FDDs. So in other words, all we have to know is for any finite collection of y's, we need to know the distribution of those random variables. Okay, so if we take a finite subset of this set of random variables, if we take a finite collection of them, then if we know all of those distributions, any given finite collection of them, then we know the law of the stochastic process. Okay? So you know the law of just one random variable, you know the law of any two random variables, and so on. So that's the stochastic process. A Gaussian process is a stochastic process where all the finite dimensional distributions are Gaussian. Okay? So in other words, if we take any finite collection of these random variables from my infinite set of random variables, okay. So if I look at y of x1 up to y of xn, for any values of x1 up to xn, then as long as they always have a Gaussian distribution with some mean and some covariance matrix, then y is a Gaussian process. Okay. So that's what a Gaussian process is. It's a collection of random variables where any finite subset of them has a Gaussian distribution. Okay. So we often write our notation here. We write y as a function. Okay, Twiddles has a distribution of a Gaussian process, a GP, okay, to denote that a function y is a GP. Okay.
Rich, just
yes.
Before you move on, in the visualization, how do you interpret the mean? Rob asks, if each dimensional sample corresponds to one line, but the Gaussians have mean, how do you interpret the mean?
Say that again, Will, sorry.
The question is, in the visualization, how do you interpret the mean? Each high dimensional sample corresponds to one line, but Gaussians also have a mean.
Yeah, so the mean here is 0 all the way across. Okay, so it'd be a constant line at y equals 0 here. So each individual, for each index here, there is a mean. Okay, so y1 has a mean, y2 has a mean, y3 has a mean, and I've set them all to be 0 here. So here you could think of the mean as being a function that's constant at 0. Does that answer the question, do you think, Will?
I think so, thanks. Sorry, I didn't spot it when you had the slide on.
Okay. Okay. So to fully specify the law of a Gaussian distribution, we said we only need the mean and variance. Okay, so if X is a Gaussian distribution, a Gaussian distributed random variable, okay, we just need to specify its mean and variance. And the same principle applies to a Gaussian process. We only need to specify mean and covariance functions. So this is back to the point, okay? Well, what's the asking? So mu is now a function, or let's say m is now a function of X, and we have what's called a covariance function, which we're going to talk a lot about. Okay? So y is a function of X. It's a Gaussian process. It has a mean that is a function of X, and a covariance function that is a function of X. Okay. So the expected value of y at any specific X is m of X, and the covariance between y of X and y of X prime is k of X, X prime. Okay, so that gives a covariance between the function at any 2 points. Okay, so if we go back to this picture here, okay, if I take index 1 and index 2, okay, so y1 and y2, they have a covariance of 0.99. And to specify the Gaussian process, we need functions that do this rather than just values, vectors like this. Okay, so we're going to see lots of examples of this. So how do we choose this mean function and covariance function? Well, we can pretty much choose them however we like, subject to some kind of basic rules. Okay. So the mean function is straightforward, so we can do whatever we like here, pretty much. Okay. So given this unlimited kind of freedom in what we choose, the most popular choice in machine learning, at least, is to pick the mean function to be 0 everywhere. So you assume your y is a random variable, and at any given location, its expected value is 0. Or another common choice is to choose it is constant, okay, so an offset. Or you might like to build in more complex things. So you could choose it to be a linear combination of x's to start to build in a kind of a linear structure. But people have done all kinds of weird and wonderful things. You can put neural networks here and all kinds of fancy features and so on. But the most common choice is just assume 0 everywhere. Okay? And there are very few rules about how you choose a mean. You can do pretty much whatever you want. The covariance function is more complicated, however. And it's the covariance function that really matters. Okay? So the covariance function we think of as a function between x and x prime. And it gives the covariance between y at x and y at x prime. Okay. And the main difficulty of covariance functions is they've got to be what are called positive semi-definite functions. In other words, they've got to lead to valid covariance matrices. Okay. So what does that mean? It means that given n different locations, so x1, x2 up to xn, then what we call the n by n gram matrix, so that's the matrix that contains all the correlations, so the correlation between x1 and x1, x1 and x2, x1 and x3, and so on. Okay, so it's the n by n matrix that contains all those different correlations. That has got to be a positive semi-definite matrix. Okay. Now, if that's true for any given choice of x1 to xn, that means that k is a positive semi-definite function. Okay. So Nicola will talk more about this later, okay, but this is kind of the key technical requirement of covariance functions. They've got to be what are called positive semi-definite. Okay. And this can be a problem. Okay. This causes us headaches and restricts the class of functions we can use as covariance functions. Okay. So you have to make various simplifying assumptions about covariance functions. And I should say in machine learning, we often call them kernels instead of covariance functions. They're called kernels. Okay. So one of the simplifying assumptions we often make is that they are only a function of the distance between an x and x prime. Okay. So covariance between y of x and y of x prime is only a function of x minus x prime. And if we do that, that results in what's called a stationary process, a second order stationary process. It doesn't matter if you translate the function left or right, it doesn't change the distribution. Okay, it's a stationary process. We sometimes go further and we assume that the covariance is just a function of the distance between x and x prime. So we've got the modulus of x minus x prime here. So it's just a distance between x and x prime. Okay. In that case, it doesn't matter what direction you point in space, it's just a distance you go in space. Okay. So we say that isotropic. So the key thing about a covariance function is that they determine the nature of the Gaussian process. Okay. So we'll talk about this more later, okay? But K determines things like how smooth your functions are, how differentiable they are. And we can think about it as defining the space in which our function lives. It defines a hypothesis space, a space of functions. And by choosing K, we choose the space of functions we want to work with. Okay, so let's just see some examples. So what I've got here are different random samples from a Gaussian process. And each sample is a single function, okay, a single line here. So this red line is one function. It is one sample from my Gaussian process. Now I've assumed the mean of all these functions is 0 here. So on average.
Richard, sorry, there is a question by William. He's asking, when do we expect non-stationary distributions?
In many situations, okay? In perhaps most situations, we expect some degree of non-stationarity. Whether we can model non-stationarity is a different matter, okay? So modeling non-stationary processes is very difficult unless you have lots of data. And so often we make a simplifying assumption to model the process as stationary, even if we think it might not be. And sometimes this matters, and we have to go away and think harder and find a non-stationary kernel. But often it doesn't. Often, given the amount of data we are better off with a simpler regression model, a stationary model, than trying to fit a highly flexible non-stationary process for which we don't have enough data to learn properly. Okay, it's a good question. So in practice, things often aren't stationary, but we don't have enough data to learn that non-stationarity, so we assume stationarity. And it causes all kinds of headaches, but it's a simplifying assumption that makes the analysis tractable. Okay. So back to this example. Each line here is a random sample. Okay. And at each location, the mean is 0. So the mean function is 0 all the way across here, it's sort of line. And then the covariance function I've chosen here is what's called the squared exponential, or RBF, radial basis function, or sometimes it's called exponentiated quadratic. Some misguided individuals even call it a Gaussian exponential covariance function because it looks like a Gaussian distribution. So it's the most commonly used covariance function, I would say. For better or worse, it's what one's often used. Okay? And you can see it produces these curves that are lovely and smooth. Okay? And as we'll talk about later, it actually produces functions that are infinitely differentiable. Yeah, because they're very smooth functions. So what we're going to do now is going to change this covariance function and see how the random samples change. So the first thing I've done is I've added a number in the denominator here. So I've divided by 0.25 squared.
Sorry, Rick, could you just explain what the values of x and y are in this plot?
Yes, okay. So x here is just my index. Okay, that's my independent variable. Okay, so I've got a function of x. The y value here is the random quantity. Okay, so x is just the index we're going to tick along. Okay, this is a function of x. Y is the random quantity. And there's a different random y at each different x. Okay. Okay, so here I've divided by 0.25. And if you think about what that does, that makes small differences between x and x prime bigger. Okay, so before, if x and x prime were distance 1 apart, then you'd get 1 squared, which is 1. Now, if they're distance 1 apart, I'm going to get a distance of, oh, I can't do that in my head, 16 apart. Okay. Now, 4 squared. So we've kind of stretched the line out, or shrunk the line in, sorry. Okay. We've magnified the effect of small differences. And so what that's done is makes the correlation fall off quicker. Okay. So instead of these slowly varying functions, we now get functions that oscillate much faster. They're still very smooth, they're still differentiable, but now they also move up and down a lot faster. Their mean is still 0. Nothing's changed in that regard. Their standard deviation is still 1. It's just the relationship between the function at 0 and the function at 1 is they're much less related than here. Okay, if you told me the function here at 0, I could take a good guess of what it was at 1. For these curves, if you tell me the value of the function at 0, it doesn't tell me much about what the function is going to be doing at 1. Let's change the length scale again. So now this number in red and the denominator here is 4. Okay, so I've stretched them out now. So a distance of 1 between an x and x prime gives a quarter here. So e to the minus quarter is 0.9 something. Okay, so it means that the correlation lasts much longer. Okay, so now if you tell me the function at 0, I could take a good guess at what the function's doing at 1 and at 2 and at 3. Okay, it tells me a lot, a single kind of observation of these curves. Okay, they vary very slowly, but still very smoothly. Okay, another way we change these covariance functions is to put a number in front of them. Okay, so here I put 100 in front, and that just changes the overall variance. Okay, so here you can think of this as being a 1 in front. Okay, so this is saying that at each location, the variance of y is 1. Okay, so all the curves fall between 3 and minus 3. Between 3 and minus 3. Okay. If I multiply
Rich,
yes.
Sorry. In the previous visualization, each index along the x-axis is one of the n dimensions of an n-dimensional Gaussian distribution. How does that translate to the x-axis and its values here?
Oh, read that again.
In the previous visualization, each index along the x-axis is one of the n dimensions of an n-dimensional Gaussian distribution.
Yes.
How does that translate to the x-axis and its values here?
Okay, good question. So here, for each index, and it's discrete here, the values plotted on the y-axis are a normal distribution. Okay. The same is true here. Exactly the same thing is true. Okay. At each location along the x-axis, if I drew a slice down here, I wish I had a tablet I can annotate. If I drew a slice through x equals 1 and looked at all those values, they would just be a normal, they would be normally distributed. They'd have a Gaussian distribution. But now, instead of having a finite discrete set of indices, I've got a continuous set of indices. Okay, so I've got an index at 1, at 1.00001, and so on. Okay, at each possible x value, if I took a slice through, I would get a different Gaussian distribution. Now, the Gaussian distributions that are at 1 and at 1.1 are closely related, and the distributions that, in the same way, the distributions at index 1 and index 2 were closely related. Okay. And here, the distribution at index 1 and index 40 are less closely related, and the same thing's true over here. Okay, if we look at two slices close together, they're similar. If we look at two slices far apart, they're more likely to be dissimilar in distribution in the samples. The distribution will be the same all the way along. It's a stationary process. Okay, but the samples will differ. Okay, so I was saying we're going from a covariance function that has a maximum value of 1. Here, the maximum this could take is 1, to a covariance function that has a maximum value we can take of 100 here. Okay. And the effect of that is to change the variance of the process from 1 to being 100. Okay, so the standard deviation now is square root of 100, 10. So all the points lie within plus or minus 3 standard deviations, give or take 1%. Okay. So now, instead of going between -3 and 3, they go between -30 and 30. So we've got these kind of 2 degrees of freedom we control on this covariance function. We might choose to use an RBF covariance function. We then have to choose the variance, the term out front, and the length scale, the number to divide it by. These 2 numbers in red. Okay. But the RBF isn't the only family, only covariance function. There are a whole collection of covariance functions. A popular choice is the Matern family of covariance functions, which is a continuously indexed family, but we tend to only use fractional powers of a half. Okay? So we things like Matern 1/2, Matern 3/2, Matern 5/2, and so on. And this is a kind of a very flexible family. This is Matern 3/2 I've given here. Okay, so you can see that all that's changed from the RBF kernel is that instead of having a squared difference in the exponential, we've got the absolute difference in the exponential. And I've also got a term out the front as well. And all that happens as we go to different families of Matern is we change what appears out the front here. Okay. Now the Matern family is interesting because it leads to samples that are not as smooth as the RBF samples. So for the RBF kernel, each sample here, each function was infinitely differentiable. Here, for Matern 3/2, each function is 1 times differentiable only. Okay. So you can differentiate it once, but you can't differentiate them twice. And if you change which particular element of Matern, you can change the degree of differentiability. So Matern 1/2 is samples that are continuous but nowhere differentiable. Matern 5/2 are samples that are twice differentiable but not 3 times differentiable, and so on. Okay. Another example of a Gaussian process is Brownian motion. So this is a non-stationary process here. You can see the distribution at 0 is different to the distribution at 5. Okay, the points spread out, and that's just got this strange looking covariance function that is the covariance between x and x prime is the minimum of x and x prime, and it gives this kind of incredibly interesting family, which you could think of as the integral of white noise. The Brownian motion is infinitely variable, and there's infinite variation. So if you look in an arbitrarily small interval here, you can find the complete works of Shakespeare written in your own handwriting. You know, there's infinite variation. If you zoom in enough, you'll find whatever pattern you're looking for. It's nowhere differentiable. Okay. Another example that's used, which isn't quite defined properly here, but is the white noise. So that's just saying the covariance between x and x prime is 1 if x equals x prime, and it's 0 otherwise. So in other words, the variance at each slice here is 1, but there is no correlation between the value between any 2 slices. So if I take a slice through 2 and at 2.1, those random samples are completely uncorrelated. So it's what we call white noise. Okay. Okay. So the Gaussian process, its nature, its properties are inherited largely from its covariance function. Which covariance function we choose tells us how fast the functions vary, what their variance is, how smooth they are, how differentiable they are. In other words, it kind of defines what space of functions we're working in. Okay. So this is a final example to give you a bit more intuition. Let's think about this covariance function k of x prime, which is just x transposed x prime, x times x prime, okay, in 1 dimensions. Okay. And if we generate random samples from the Gaussian process with this covariance function, we get straight lines through the origin. Okay, so if I have a zero mean Gaussian process with this covariance function, these are different samples, straight lines through the origin. So the question is, why is that happening? What's happening here? Okay. Well, to think about it, let's suppose we assume the model that y of x is a constant times x. So in other words, a straight line for the origin. And let's give C a normal distribution, mean 0, variance 1. So the gradient, our distribution mean 0, variance 1. Okay. So this is a Gaussian times x. So y of x has a Gaussian distribution for any x. So it's a Gaussian process. So we've just defined a Gaussian process here. If we think about its covariance, what's the covariance between y at x and y at x prime? Well, this is the covariance between c of x and c of x prime. Okay. Well, x is constant, so it can come out this covariance. So we get x transposed times the covariance of c with c times x prime. Well, that's just the variance of c, which is 1. Okay. So the covariance between y of x and y of x prime must be x transposed x prime, or x times x prime in this 1D case. Okay. So what we've said is that if we define y in this way, then in other words, y is a Gaussian process with mean 0 and with covariance function given by this. Okay. So if we use this particular covariance function, a linear covariance function it's called, we get straight lines through the origin. Okay. So I'm going to pause for a couple of minutes for questions. Okay. And then we'll talk about why we might want to use Gaussian processes. Will?
Sorry, just an immediate question from your linear thing is it possible to fix a slope in the linear kernel rather than the variance?
Say that again.
So is it possible to fix the linear, like the slope of the linear kernel rather than just the variance of the linear kernel, is the question.
Is it possible to fix the slope rather than variance? I'm not quite sure what that means. We can certainly change these numbers in here. So instead of having 0, 1, we could give it a mean and some other variance, and that would change the sample of functions we get. So here you can see.
Sorry, it's clarified. Is the slopes of the lines from the samples, so making all of the samples the same gradient?
Yeah, and just change the offset. So we can do that certainly. So we can give it a random intercept instead. Yep. So that's possible. I'm not going to try and work out the details. I can't write on screen, so it'll be difficult to explain. But I'm happy to talk about that this afternoon. But yes, you could have what's called a bias kernel, which is just a constant. So if you made the covariance between x and x prime just a constant, that gives a random mean and a random offset here. So yes, we could do that.
Okay, thanks. And just some more general purpose questions. So I think the most popular one is, you're using a 0 mean for the GP prior. When would using a non-zero mean be useful, and could you provide some examples?
Yes, certainly. So if you're modeling a process where you know there's a trend, it makes sense to include that trend in your mean function. Okay, so often, so I'm into computer experiments, so kind of models scientists build. Okay. So often they might know the behavior of the system up to first order, up to second order. Okay. They might know there's a kind of linear trend with X, and that we're using the Gaussian process then to pick up any deviations from that linear trend. Okay. Okay. So yeah, so you know, one thing we might do is model. You can do more complicated things. You can model the trend as some complex set of differential equations. That's your mean function, and your Gaussian process picks up your deviation from that complex model. But there are lots of examples where you might want to use non-zero mean. I think the reason in machine learning people tend to use zero means the type of problems that they look at are often very data rich, okay? And they're you know, traditionally at least, they're not they tend to look less often at kind of science and engineering problems where you have that kind of trend going on. That's changing all the time. So, yeah.
Thanks. And another common question is how would you choose what covariance function to use?
So I'll talk about that a bit later, but basically trial and error. Okay. So there are ways of automating these things and doing them better or worse. Okay? But often we might, you know, whatever your favorite type of procedure is, so whether you're a Bayesian or frequentist, you would estimate your hyperparameters using your favorite kind of approach, so maximum likelihood, or whatever. And then you might choose between different classes of covariance function by tests on held out data. So you split your data into training data and test data, you fit it on your training data, and you see how well an RBF kernel predicts. We see how well Matern predicts on your test data. Or you do cross-validation. But generally, as Nicola will talk about later, it's kind of a user-guided process of trial and error where we try different things, and you can build up all kinds of weird and exotic, wonderful covariance functions by multiplying them and adding them and transforming them, warping them. Okay, but it's essentially a case of trying and seeing what works well.
Okay, and I guess the last question for this midsection. What do you mean by differentiability of the function? Why is that important? And how does that relate to different choices of the kernel, particularly the distance function that you add in the kernel?
Okay, so we're modeling functions f of x. Okay, and one way we one thing that defines what the function looks like is how smooth the function is. So with Brownian motion here, this is a continuous function, almost everywhere continuous, but almost nowhere differentiable. Okay, so you can see that you get these very rough functions. In contrast, from the RBF, we have functions that are analytic. They're infinitely differentiable. They have derivatives of all orders. Now, analytic functions are incredibly smooth and unrealistic. There's some strange facts about analytic functions. So if you told me the value of this function at a location and all of its derivatives, yeah, so you told me the first derivative, the second derivative value, third derivative, so on, just at one location, then I could tell you what the function looked like everywhere, all through space. Okay. So they're a very kind of special class of functions, analytic functions, and unrealistic for many kind of statistical problems. So they're very smooth and it creates problems. So you know, the degrees of differentiability just determine what the function looks like, what it feels like, how smooth it is, okay, how rapidly it can change. A Matern 3/2 function can change direction quite quickly. It's only got one derivative. So if you think about it, to turn it round, you just have to wait for its derivative to come around. The derivative is a continuous function, and so its derivative changes direction. For a Brownian motion, the derivatives aren't continuous, they don't exist, okay? So it can change direction on a whim, yeah? At one location, it just changes direction straight away. With an RBF kernel with infinite derivatives, it's very slow to change direction because all the derivatives have to come around, okay? And so, you know, the degree of differentiability really determines the nature of these functions. Okay, does that answer the question, do you think, Will?
Yeah, I think that's fairly comprehensive. I'm sure if there are more specific questions, then participants can either ask them or talk to you in the roundtable later.
Okay, I'm just going to turn my email off, stop it bouncing. Okay. Okay, So why do we want to use Gaussian processes? Why use this very restricted class of models? Okay, we're restricting ourselves to Gaussian distributions only. Why would we do that? Well, it's because they've got several properties that make them easy to work with. Okay, and so to begin with, let's think about Gaussian distributions. Okay, so Gaussian distributions have several properties that make them easy. So first of all, if Y is a multivariate Gaussian distribution with mean mu and variance sigma, okay, well, that is true if and only if for any matrix A that we can multiply Y by, okay, if that has a Gaussian distribution where we just multiply the mean and the variance. Okay. So if Y is Gaussian, multivariate Gaussian, then A times Y must be multivariate Gaussian with mean A mu and variance A sigma A transposed. Okay. So that's nice. It's saying sums of Gaussian are Gaussian. Okay, so if we took A to be a row vector of ones, A times Y is just the sum of all the Y's, the sum of Gaussians. So that's saying the sum must be Gaussian. It also says that the marginal distributions must be Gaussian. So if we took A to be 1, 0, 0, 0, ... Okay, then A times Y is just the first element of Y. So it's saying that must be Gaussian. Okay, so this is a nice property. I mean, they're nice to work with. Okay? And this is where the kind of positive definite thing comes from. Okay, we must have the variance matrix sigma to be positive semi-definite, as we know we must have for any vector A in RD, we must have that A transpose sigma A be positive because it's got to be a variance, a valid variance according to this. Okay, so that's why we have this requirement for positive semi-definite functions. Okay, I'm going to skip that. Okay, another reason we like Gaussians is that conditional distributions are still Gaussian. So let's consider a two-dimensional Y. Okay, so a Y that's multivariate Gaussian with just two components, Y1 and Y2, where the mean is mu1, mu2, and the variance matrix sigma is given by these elements. The nice thing about Gaussians is that if we observe one of them, if someone comes along and tells you the value of Y1, you're told its value is lowercase y1, then it changes what we think about Y2. And the nice thing is that what we now believe about Y2, given that piece of information about Y1, is still that it's a Gaussian distribution. So to begin with, we thought that Y2 was normal with mean mu2 and variance sigma 2. Once you are told the value of Y1, you still think it's Gaussian, but you just change the mean slightly. Okay? And you change the covariance in a way that we're going to derive in a moment. Okay. So I think it's instructive to see where this comes from once. So I'm just going to go through the details a little bit so we can see this, and then we'll build up to Gaussian processes. Okay. So we want to think about, we've got two random variables, y1 and y2, and we want to ask what's the distribution of y2 given the value of y1. Okay. Well, that's the distribution of y1 and y2 divided by the distribution of y1, just the definition of conditional probability. And all we need to do is keep track of the y2s here, okay? Because this is an integral of y2, so we just need to keep track of all the y2s. So that's going to be proportional to y1 and y2, the joint density. So let's write out the density for a multivariate Gaussian. We had this was the probability density function. It's in this quadratic form in Y, so we've got Y minus mu transpose sigma inverse Y minus mu. And if we write that out in full, okay, where I've called Q here the inverse of sigma, okay, what we end up with, if we get rid of all the terms that don't have a Y2 in, is just an exponential that has a Y2 minus mu2 squared, if you like, so y2 minus mu2 transposed q22 y2 minus mu2 plus the cross term here. Okay, so we got a y2 minus mu2, a q21, and a y1 minus mu1. So what is this? Okay. We're thinking, can we recognize this distribution, this line, as a valid distribution for y2? Well, this is just a quadratic in y2. So e to a quadratic, we know is a Gaussian. Okay. So this tells us that y2, given the value of y1, is still Gaussian because it's still e to some quadratic term. Okay. And if you work through the details, we can figure out what the mean and standard deviation are. I'm not going to go through that now. You can look at that kind of offline. The slides will be made available if they're not already on the website. Okay, but if you work through it, we get a particular distribution for the updated mean, okay? And we get a particular distribution as well for the updated variance. So to summarize, if we've got a multivariate Gaussian and we observe some components of it, then the bits we don't observe are still Gaussian. Okay. So let's think about this for Gaussian processes now. That was for Gaussian distributions. So for Gaussian processes, we've got functions that have an index. Okay, so sorry, I've switched to f here for my function. So suppose f is a Gaussian process. Then if we take f at any finite collection of points, so I've got the points here x1 to xn and x, then we know that jointly they have a multivariate Gaussian distribution. Okay. And the key kind of observation we're going to make is that if we observe the value of f at some location, so if we observe f of x1, f of x2, f of xn, so we observe the function at some locations, then the distribution of f at some other location x is still going to be Gaussian. Okay. All we do is we update the mean and variance, okay, like we did on the previous slides. So what does that mean in terms of pictures? Okay, so here I've got prior samples from my function on the left. Okay, so I've just like we had before, I've got random samples of distributions drawn from a Gaussian process. They go up and down, you know, they are continuous functions. We're going to observe the function here at 1, 2, 3, 4, 5 locations. In the middle plot, you can see these 5 dots. Okay, we're going to observe f at x at 2, x equals 2, x equals 4, x equals 6. I can't see where they're quite at 7 and at 10. Okay, so we observe the function at some locations. The nice thing is that our uncertainty, our belief about f, given these observations, is still a Gaussian process. Okay. We've just now changed its mean and covariance function. So instead of whatever mean and covariance function we had before, we've got new means and covariance functions. So let's see this in more detail. Okay. Sorry, I'm just going to. Okay. So just to summarize then, we'll see some more plots in a second. You know, one reason we like Gaussian processes is that it's closed under various operations, under any linear operation. So one thing that we can do, if we take 2 Gaussian processes and add them to each other, so if f1 is a Gaussian process, some unknown function, f2 is a Gaussian process, some other unknown function, then if we add f1 and f2, they're still Gaussian processes. Okay. The property I've just been talking about is that they're closed under what we call Bayesian conditioning. So in other words, if we observe some data, if we observe f at some locations, then our model for f is still a Gaussian process. F given d is still a Gaussian process, but with new mean and covariance functions. That's all that's changed. So mathematically, that's very nice. We can do things to these Gaussian processes, and it doesn't change the fact that they're Gaussian processes, just changes the mean function and the covariance function. A bit more advanced, and we won't talk about today, but we can do this with any linear operator. Okay, so if f is a Gaussian process, then if L is a linear operator, L applied to f is still a Gaussian process, where we just apply the linear operator to m and to each input to k. Okay. So in particular, that means we can differentiate Gaussian processes. We can integrate Gaussian processes, and they remain Gaussian processes. And that is not true for many or if any other process. Okay. So we can do all these different things to them mathematically, and we remain in this family of Gaussian processes. So to spell out the conditioning a bit more then, let's go back to the example I had a moment ago, where we've got x1, xn, and x. We observe f at those locations. Okay, we're going to observe f at x1 to xn, and we're going to predict what f is at some generic location x. Well, if f is a Gaussian process, then we know that that joint, so that notation isn't very good there. We know that joint vector, I should have brackets around these, the vector here, has a multivariate normal distribution with mean 0 and variance matrix sigma, where sigma is just given by our covariance function. Okay. So we've got the first element is the covariance between x1 and x1. There's a bracket missing, I apologize. Okay. Down to x1, to covariance between x1 and xn. And the last column here is covariance between x1 and x. Okay. And so on down. Okay. We're going to split this matrix into terms. Okay. So this bit here, the covariance between all the observations, all the x's that have indexes here, I'm going to call capital K subscript capital X, x. Okay. So that's the gram matrix. That's the covariance between xi and xj. This vector on the side here, okay, so this is a column vector. That's the covariance between x1 and x, x2 and x, xn and x. Okay, so I'm going to call that k subscript x evaluated at lowercase x. Okay, the prediction location. Okay. The summary of what we've kind of been working through with Gaussian distributions says that if we observe f at x1 to xn, then the distribution of f at any location x, given those values, has a normal distribution with mean m bar and covariance or variance k bar, okay, where the mean is given by k subscript x, the values of x transpose, times the gram matrix, the inverse of the gram matrix, times the vector of observations. So this is just a linear combination of this vector of observations here. And the variance of f is similarly, it's just the prior variance k of x and x shrunken a bit. We subtract a bit off. We subtract off kx of x transpose the inverse of gram matrix kx of x. Okay. So these formulas are not very intuitive. Okay, you don't kind of obviously see where they come from. So what we're going to do in a minute is kind of motivate them. But the point I want to make is that the distribution of f at some test location x, given some observations, is still just Gaussian. All we've done is change the mean function. The mean function has gone from 0 here to m bar, and the covariance has just gone from whatever covariance we had before, k, to k bar. Okay. And to state this more generally then, if we have a prior mean function, so rather than the 0 mean function here, if a priori f is a Gaussian process with mean m, covariance function k, then given some observations, we update to m bar and k bar, where the new mean m bar is just the old mean plus a bit, and the new covariance k bar is the old covariance subtract a bit. Okay. And that's all we have to do. Okay. We have these observations. All we have to do is a bit of linear algebra. This is a matrix inverse times a vector times a vector. Okay. This is a vector times a matrix inverse times a vector. So it's very simple to update the mean and covariance functions here. Okay. So how do we normally plot these things? How do we normally think about these things? Well, let's just have a look here. I've got a Gaussian process and I've observed this at 4 locations here. And what I've plotted is the posterior mean function, m bar. Okay, so that's this solid blue line here. That's the posterior mean function. It started at being 0 everywhere, and now it's non-zero in most places. And then I've also plotted the shaded region, which is my 95% credible interval. So that is the mean plus or minus 1.96 times, sorry, it should be the square root of k there, shouldn't it? The square root of the variance. Okay. And so that gives me my credible region. Okay, so we've still got a Gaussian process, but now we know something. We know its value here, we know its value here. And in between those points, we're quite confident of its value. There's some uncertainty in here, but not a lot. Okay. In practice, we don't normally observe functions directly. Often we might have noisy observations. We might observe y, which is f of x plus a bit of noise, plus a bit of Gaussian noise. So I've assumed 0 mean Gaussian noise with variance sigma squared. And the only way that changes the calculation is we still have that y1 to yn and f of x are still multivariate Gaussian. But now we change the matrix from before. Instead of having just k xx in here, we've got k of xx plus a diagonal matrix sigma squared times the identity matrix. Okay. We've got, if you think about the distribution of y, it's a distribution that comes from the Gaussian process model for f plus this independent noise term. So that's why we get sigma squared I here. And if we update, we get the same kind of looking formulas as before, but now instead of having kxx inverse in here, we've got kxs plus sigma squared times the identity inverse. Okay, so that's all that's changed when we got noise. We just add in sigma squared I here. Sorry, a bit flipped off the screen there. I'll fix that.
Rich?
Yes.
It would be quite expensive to invert big kxx, right? If we have a large amount of data.
Yes.
Would you say this was a common problem?
Yes, it's a very common problem. And in practice, we don't invert k. Okay, we solve it more efficiently with I don't know, a computer scientist can tell you. But it's still a problem. Okay, we essentially have to invert this inverse of k times a vector. And the problem with computing inverses is that they cost, the cost scales with the cube of the number of observations. So if you've got 1,000 observations, that's already a billion kind of calculations, order of a billion calculations you have to do. So the cost scales very quickly with Gaussian processes, and that's a problem that lots of people will talk about during the week. Okay, but yes, it is a problem. So if we have a nugget term, a standard deviation term, so if we have noisy terms here, previously here we were interpolating the data points because we were observing f exactly. So my posterior mean was exactly going for the points. There's no uncertainty. But now if I have noisy observations, we no longer interpolate the data. So here we've got a curve that doesn't quite pass through all the points, okay? And the uncertainty doesn't collapse to 0 at any of the points. Okay? We've got a standard deviation, which is sometimes called a nugget of 0.1 here, so which we've got kind of error bars around the observations. If I make the nugget term or the variance smaller, these bars shrink. Okay, we get more confident, we get closer again to interpolation. Okay, I want to skip that point. So are there any questions at this point?
Yeah, so does the posterior mean always pass through the data points you're conditioning on?
So not in this case, okay? So in this case, where I'm assuming my observations are of the function plus noise, then we don't interpolate. But if we use this structure, so if we assume we directly observe the function, then yes, it will always pass through the points. It will interpolate the observations. So it depends upon the details of your kind of observation model.
Okay, and if you have noisy observations, do you always assume Gaussian noise?
No, not at all. Okay, if we assume Gaussian noise here, then y remains a Gaussian process. But just as in the same way we go from linear models to generalized linear models, GLMs, okay, and we have, you know, logistic regression or Poisson regression, we can do the same thing with Gaussian processes. So we don't have to have Gaussian noise here. And we can do, you know, logistic regression and so on, but it means that our observations aren't then a Gaussian process. And so the mathematics is more complicated. We can't do things exactly. We don't have an exact formula for the posterior. We have to take other approaches. And people, I believe, will talk about that tomorrow morning when we have non-Gaussian likelihoods.
And how would you update a GP regression fit with new data? And is it quite computationally cheap to do that?
Yes, so essentially all you have to do is these formulas each time. Okay, so given a covariance function, you update it to a new covariance function, where the generic expressions, I'll use these. Okay, you update it just using these formulas each time. You get more data in, you update it similarly. And if you've got data coming online sequentially, then there are cleverer ways of doing it than this, cheaper ways of doing it, but that's essentially it. You just take your old mean function, you compute your new mean function, you take your old covariance function, you compute the new covariance function. It doesn't change at all. Okay.
Just to clarify, do you throw out your previous inverted matrix if you discover more data for KXX?
You won't be able to use the previous one directly. You'll have to update it in some way. Now, if you just have a small number of new observations on, there are efficient ways of inverting a matrix if you know the inverse already for part of a block of that matrix. But yes, you could just throw it all away and start again. That would be the simplest thing. But you know, there are more efficient ways, but not so straightforward if you've got things coming on sequentially.
And then just a point on data pre-processing. So some people have observed that your data's been pre-processed, like normalized with the standard deviation. What kind of transformations would you recommend for pre-processing your data to fit with GPs, and how much of an effect does that have on learning the GP?
So, I mean, that's quite an advanced question, and Nicola might talk more about it. The most common transformation is just to center and scale your data. So to transform it so that it has mean 0 and variance 1. And that doesn't really matter, doesn't change anything anything theoretically about your model at all. But how it can help is in your optimizer that you use to find the hyperparameters. So I will have to go a long way back. Before we had these hyperparameters in our covariance functions. So, you know, these red numbers, the length scale and the variance, we're going to estimate them. And often, you know, the optimizers have been developed and trained using data where you expect the mean to be about 0. You expect the standard deviation to be about 1. You expect the length scale to be about 1. Okay. So if you kind of put your data in a format, center and scale it so that the optimizer is looking in the right place for these hyperparameters, that often helps in practice in software, but it doesn't change your model at all. In terms of non-linear transformations, you might want to do that to make things look more Gaussian, just like you do normally. So logging your data, if it's over many orders of magnitude, can often help. And all the other things we do in regression modeling may help in just the same way they do with Gaussian processes, just the same way they do in linear modeling. But it's just changing what you're, where you are assuming is a Gaussian process. So if you model the log of your data, modeling the log of the process is a Gaussian process. You just have to, you know, there's nothing magic about this. You just have to see what works. Okay. Any other questions, Will?
Yeah, so just in terms of the nugget term.
Yeah.
How do you choose the nugget term? how do you choose the size of it? Oh, that's it. There's only 2 questions. So
Yeah.
I said that like there were 3.
So again, you can estimate it in your optimizer. Okay, so you can set it as a free parameter and you estimate it by maximum likelihood. But often you know something about your measurement error. Okay, so often if you're doing an experiment, you know how noisy your measuring device is. So you might want to specify it, but if not, you can just estimate it. So just as you would any other high parameters. So you'll see this in the lab session this afternoon. Okay, so we'll show you in the labs how you estimate these things.
Just one final point I just noticed on Hoover. A couple of people are confused about whether x going into kxx is scalar or vector valued, because in the linear kernel you had x transpose x. Yeah, just could you clarify that, please?
I've been a bit sloppy in places, so it can be either. In general, it won't be. It won't be scalar, it'll be a vector in general. Okay. And then we just write down vector versions of the covariance functions. Okay. So the covariance function takes 2 vectors and gives you a scalar that is a covariance between the function at those 2 locations. Yeah, so sorry for that uncertainty. Anything else, Will?
I mean, for now, just carry on because I'm just going to curate the rest of the questions.
Okay.
Just a lot coming in, so
yeah. So I'll go quite quickly, I think, through a couple of the motivations, okay, and then I've got way too many slides, so I won't go through them all, okay, and then we'll take some questions at the end. So we've had one answer for why use Gaussian processes, okay, and that is that it's a mathematically tractable family that is closed under Bayesian conditioning and under linear operations, and that makes it nice. Okay, so we can work out the posterior exactly without resorting to Markov chain Monte Carlo or anything complicated, okay, in the basic case. Another motivation for why I use GPs is you can think of them as a non-parametric extension to linear regression, or as being a special case of kernel regression, but with uncertainty. So the kernel K determines the space of functions that sample paths live in. Okay, so let's suppose, just think about linear regression for a minute. So let's suppose we're given data xi, yi, okay, and we want to fit the model x beta. Y is x beta. So one way we would do this would be least squares regression, where there we might minimize the sum of squared errors. Okay, so this is just the L2 norm or the sum of squared errors. Okay, the difference between y and my prediction x beta, and we'd choose beta to minimize the sum of squared errors. That would be my optimal beta, beta hat. Now, if we have lots of betas, we often do what's called a regularized least squares, or it's called ridge regression or Tikhonov regularization. Okay, and we add a penalty term here that just adds up the sum of the squares of the betas. Okay, and that ensures the betas can't get too complicated, and it restricts our class of functions. Okay, and helps with out of sample prediction. So you probably all learned in your undergraduate statistics classes, second or first year classes, that the optimal beta here, the best value of beta has got this simple expression, so x transposed x plus sigma squared I inverse x transposed y. Okay, so that's our least squares estimator, or our regularized least squares estimator. Now we can rewrite this into what's called the dual form. I won't go through the maths here, you can look at this on the slides offline. Okay. But just by slightly rejigging things, we can go from inverting a matrix that's x transposed x plus a diagonal to x transposed. Okay. So this is called the dual form of the solution to the optimization problem. So why do we want to do that? Okay, because if we look at this here, it looks like it's made life harder for us. This is the normal solution you see. This involves us inverting a P by P matrix. X transpose X is P by P, where P is the number of parameters in our space. Sorry, that should be a P there, shouldn't it? This involves inverting a matrix that is the dimension of the number of features we have. Whereas the dual form has X x transposed in. That's n by n, where n is the number of data points. Now, in most problems, we're going to have way more data points than features, than covariance. Okay, so n will be bigger than p. Okay, so the dual form of the solution is doing more work. Inverting an n by n matrix will be harder than inverting a p by p matrix in most cases. But if we look at this dual form, okay, we'll see it's the same as the Gaussian process updates. Okay. So if we look at x transposed, that is just a collection of inner products. So we've got x1 transpose x1 up to x1 transpose xn. So that works out to be the same as the gram matrix we had before in the special case, in a particular case where we choose our covariance function to be the linear case we had, x times x prime. And if we look at prediction for a new location, so if we predict y at new location x prime, so we do x prime times beta hat, then we can write it in exactly the same form as we had for our Gaussian process updates before. Okay. So this equation here is exactly the same in the special case where k is x prime. Okay. So what we've said here is that linear regression and Gaussian process regression are equivalent when the covariance function k is x times x prime. Okay, so they're equivalent. They're doing exactly the same thing in terms of the mean function when we have that covariance function. Now, we all know that when we do linear regression, instead of just using x, we can replace it by features, higher order powers of x. Okay, so instead of just using x, I could have a feature vector that is 1x and x squared, say. Okay. And this doesn't change at all the calculation of how we do linear regression, apart from I change this kernel function from being x transposed x prime x, to phi of x prime times phi of x. Okay, all I have to do is replace x by the features of x. And exactly the same mathematics works. Nothing has changed. Now, the clever thing is, for some sets of features, computing the inner product, so phi transpose phi, that's an inner product, okay, doesn't require us to evaluate the individual features. Okay. So, for example, let's suppose my feature vector phi, where the index space is two-dimensional, it just has all the first order powers, second order powers, and the first order interaction terms. So I've got an x1, x2, x1 squared, x2 squared, and x1 times x2. Okay. So to compute, if you work through this, you've probably seen this before, but to compute the inner product between phi of x and phi of, I'll call it z here, z prime, okay? All we have to do, it turns out, is to compute the inner product between x and z and square it. 1 plus the inner product x and z. So to compute the inner product here, we don't actually need to compute the set of features at all. We don't need to write out these 1, 2, 3, 4, 5, 6 features. All we have to do is to do the inner product between x and z and square it. Okay, and that will give us quadratic regression, if you like, linear regression using all the first and second order terms. Okay, so that was with a 6-dimensional feature vector. But the same idea works sometimes when we have an infinite dimensional feature vector. So we can have a phi of x, a set of features that is infinitely long. Okay. In fact, there's a theorem, okay? It says that if k is a valid covariance function, then we can write it as an inner product between a set of features, okay? And vice versa. So if we consider a set of features, the inner product between those two sets of features is a valid inner product, and vice versa. Okay. So this gives us another way of thinking about Gaussian process regression. We said that GP regression, linear regression was the same as a Gaussian process with a linear kernel, and the same is true here. Okay? We can think about Gaussian process regression with some kernel k as being linear regression with some set of features phi of x. And the clever thing is that for many covariance functions, the features corresponding to k are infinite. So I'll just go through this final slide, then I'll summarize. So let's think about the RBF kernel. Okay. If we think about a set of features, okay, so if I just restrict my input space to be 0, 1, and I'm going to put a grid out at 0, 1 over n, 2 over n, up to 1, then if I let my set of features be Gaussian humps centered around each of these points, okay, so I've got a feature vector of length capital N here, then the inner product between a feature vector phi of x prime and phi of x converges towards the RBF kernel. Okay, so when we're doing Gaussian process regression with this RBF kernel, we can think of it as like doing linear regression with Gaussian humps. Okay. So this is what we think of as the kernel trick in machine learning. We can write down, or we can think about this infinite dimensional feature vector. And because we only ever need to evaluate inner products, we get regression very cheaply using the kernels instead. Okay. So I've run out of time, but just to say that the kernel is what, don't look at the slide, the kernel determines the space of functions we're working in via these features or via other representations. So by choosing the kernel, we're choosing a set of functions, and then we can just think of it as doing linear regression essentially in that space. Okay. So then, just to summarize, I noticed we've got almost 300 people here, which kind of bears witness to the fact that Gaussian processes, which were 10 years ago, or 20 years ago, a fairly niche area of statistics, known to very few people, have become ubiquitous. You know, once they're only brought out on special occasions, they're kind of the good china, if you like. Now they're used widely in statistics and machine learning. The reason they're popular kind of stems from the naturalness of the framework. Gaussians appear all over the place. Okay. Their tractability, we can work mathematically with Gaussians. We can fit them to data. Okay. Gaussian processes, it works nice. And finally, which you'll see more of this week, their empirical success. You know, in no end of applications, people have had great success using Gaussian processes as data models, and that's led to them being kind of widely adopted through many different communities. Okay, so I'm going to stop there, and I'll take any final questions you have.
Yeah, hi. Thanks for all that, Rich. I think a big theme in a lot of the questions, and I'm trying to calculate, is that what's the main advantage of GPs over other methods? And particularly, how does it relate to other kernel methods like SVM or reproducing kernel Hilbert spaces? And why would you use GPs over other methods?
Yes. Okay. So let's deal with the reproducing kernel Hilbert space question first. So I know I've not talked about this. Okay. So the idea behind reproducing kernel Hilbert spaces is that you define a space of functions you're going to work in according to your kernel. So you define your Hilbert space, which is essentially the span of all the functions that arise from your kernel. And then to pick the optimal function from that RKHS, that reproducing kernel Hilbert space, you solve this regularized least squares problem. Okay, so just like before, you choose F. Sorry, you choose F from your space of functions to minimize the squared error plus a regularization term that stops your function getting too complicated. And it turns out that the function you estimate in kernel regression is, under some assumptions, exactly the posterior mean of the Gaussian process. So the posterior mean of your Gaussian process is doing kernel regression. What a GP gives you, which kernel regression doesn't is uncertainty estimates. Okay, so we can think of any prediction as a point estimate plus uncertainty. So the mean of our Gaussian process is our point estimate, our best guess. That corresponds with kernel ridge regression. What it also comes with is uncertainty, a variance. Okay, so we get a variance of our prediction, not just the mean. And that's what distinguishes it from non-probabilistic methods like neural networks, for example, or kernel regression. They're non-probabilistic, so you have to do a kind of additional procedure to get uncertainty. Here, the uncertainty in Gaussian processes is part of the procedure. It comes for free, if you like. Does that answer the question, do you think, Will?
Yeah, I think the questions about particular kernel methods that covers that. And then the next bit was kind of why you'd use GPs over other methods, I guess. Yes.
So I think, you know, no one method always beats any other method. If I had a problem with tens of millions of data points, I probably wouldn't start with Gaussian processes. But if I have a problem with thousands of data points, then, you know, experience of the community kind of shows that Gaussian processes are very competitive in those low data regimes. They're very kind of effective ways of thinking about data. They're intuitive. We get uncertainty. They seem to work well. So, you know, why use GPs over other methods? It depends on the situation, but they've been successful. They're often worth a try, I think.
Thanks. And then just a question on stability. A few people had questions about what happens if your observations cause you to have an invalid covariance matrix. I mean, what if you have two observations in the same location with different values? How do you handle stuff like that?
Yeah, so if you've got two observations at the same location with different values, you must have a noise term. Okay, there must be noise there. So often, if we're using, let me find the relevant slide. Often when we do this matrix inverse in here, we will get an error message because K might be ill-conditioned. Okay, its condition number might be close to 0. It's if you've got collinearity in your data and so on. It's a very common problem. And the way we fix it is to add a noise term. Okay, so adding in a diagonal element on here makes this matrix better conditioned. Okay, and in practice, what we do, even if there's not noise, is add a small amount of noise, often called jitter. We add just enough to make the matrix invertible. Okay, so yes, numerical stability is a problem with these things, particularly with the RBF kernel, because it's so smooth, collinearities appear very quickly. Okay? So it is a problem, and the way out of it is to just kind of add what's called a jitter, a diagonal term like this.
Thanks. I think we're kind of out of time for questions. I know I've told some people that I'd ask the questions, but we've just run out of time. I'd like to remind participants that there'll be roundtables from 1:45 to 3:30. So if you have any questions, you can ask the speakers. You can also use the Hoover app to ask questions, and I'll direct Rich to that. Also, from a practical sense, remember there's lab sessions this afternoon, so you'll be able to play around with some of the more practical things. But yeah, thanks, Rich, for giving the talk.
Yeah, thank you.
Mauricio, I don't know if you want to say anything.
Yeah, so thanks again to Rich, and we're gonna be we're gonna have a coffee break of 20 minutes before we start the next lecture. And as Will was saying, there will be more space to ask questions in the afternoon, and also in the Huba chat. So you understand that we can't really take all the questions because otherwise we wouldn't do any lecture at all. So just be patient. I will try to get your questions, but please go ahead and take a break because usually these sessions get to be very tiring in the long run. So take a break, and we'll be back in 20 minutes with the next lecture by Nicolas. Thank you, Richard.
Rich, you're still sharing your screen.
How do I stop sharing my screen? That's the question.
Oh, I can just do it. I'll do it for you.
Thank you.